Hello, welcome. So in this series, we're building a data-oriented compiler in C. In the previous episode, we built out this IR here, and it's working pretty good, but I was a little bit perplexed at the code that it was generating. If we look in the tests here, this is in the wrong order. And I was kind of put off by that because I was expecting this to be really easy to translate into machine code without having to have a sophisticated register allocation thing going on. So I was out on a walk, as is often the case, and it just hit me. I wonder if we're parsing on the wrong side. And sure enough, I tried it out, and really all I needed to do was convert this back to parse primary. This was parse binary before, and then add a for loop around this, basically. And that's it. And lo and behold, when I do this, the tests fail, of course, but the code generated is exactly how I would expect it to be. So I was complaining here. Let me just make this a little bit bigger here. I was complaining that V0 should be right before where it's used here in V4. And that's exactly the case now. It's now V3 and it's used right there. And then I was saying that for the subtract, for the add, V3 is on the right-hand side, and that makes it difficult to use the same register for all of these instructions. Well, now V2 is on the left-hand side. And so figuring out how to do this is going to be really easy. So I think left-hand recursion is actually what you're supposed to be doing, which is what this is. This is now just recursing on the left-hand side, just by using for loop, basically. So I think this is what is supposed to be done. I vaguely recall something about left recursion and that's what you're supposed to do, and that this was the solution for it. But yeah, you're supposed to build out on the left-hand side of the tree. And then for prep parsing, you would occasionally have to put things on the right-hand side, but generally it would be on the left-hand side. So yeah. So now the tests aren't passing because the tree is being built on the other side, the correct side. So we got to fix those. That should be quite straightforward. So which one is add 3 and 5, subtract 7 is failing. This one here is failing. So that should pass now. If I make sure there's a comma where it's supposed to be, and remove a comma where it isn't supposed to be, that passes. All right, and then we got to fix the other one. All right, so just to be really clear on what I changed here, what ends up happening when this is executing is it first parses a number. So let's say we have this. First, it will parse this 1, and that'll be parsed right here. Then it'll go into this for loop, and it'll parse the plus here. So it hits this, and it inserts a node, and it reserved the position right before this 1 as the place to insert that, but it didn't insert it yet. So it'll end up inserting. So you'll end up with these steps, basically. Literal 1, and then the second thing it'll do is parse the plus and it'll go binary add right in front of this literal, and then it'll have, and then it will hit this parse primary here and end the node. So this literal one is already there, already at this point in the array. And then it will hit the literal 2. So it'll be basically like this, and then add in the literal 2 after that. And then it'll loop back up to here. It'll check to see what the next token is. The next token is a minus. And then it'll hit this node, or it'll hit insert node. Insert node is still pointed at the very beginning. So it's pointed before this binary. So it'll do this. And then all of this will be there. And so that's what happens when it hits this. And then it'll parse another primary. And the other primary will be this 7. So then it will add the literal 7 here at the end. It will then loop again. It'll hit this. It'll hit this default because it's not an add or a sub token. And it'll hit this left and just return it. So then it'll return this entire thing. So that's what's happening now. And I think that's what it's supposed to be doing. So then the code that it generates is a lot easier for us because we don't need as sophisticated of a register allocator. In fact, we can kind of almost cheat. Very similar to how we're cheating here. We're just always using A0. We can actually just do that. So we should be able to get this kind of code generation working fairly easily. So I think we should try and do that. Yeah, I think as usual, we'll be just working in this file here. Now, what do we need? This is generally called the code generator. But first we need, I guess, the registers, but I think we can skip register allocation completely now that the code's in a better place. So this would become a move of 3 into A0. This would be just moved right here. So we would, how would we do this? We could probably just ignore these completely. And when it hits this, it'll move this. It'll generate a move instruction maybe. And then when it hits this, V2 will already, how would we do this? Like, I almost wonder if it would be a little bit more clear if we made these just print inline. Let's actually just start with a test case and see what is the simplest thing that could possibly work. Okay, so the first one passes, but the other ones I don't think are going to pass. But what I did is, basically just had AI generate this. It's just a function that's generating from the code. So for the first test case, we basically just have 42 going into it, and it's going to generate an op int, which is just a constant, and it'll hit this code. And then the other one is op error, so it'll hit this code, and then it should go through. So that's corresponding to these. So this will become a move instruction, and then this will just become the error instruction, and that should work. And it does, it passes. So it produces this code, which is what we want. It'll get more complicated though once we move on to the second case up here. So that would be 2 plus 5. And that will not work. I'm just going to modify this test case because we're going to be replacing this with table tests after this anyway. So yeah, no, this is not correct. So this shouldn't generate code. And then this one, okay, that seems to work. So all I did was just ignore this. And if the left-hand side is an op int, then it generates the move instruction. Otherwise, it just chains it from the previous instruction. So there's a lot of assumptions here, and I've kind of asserted one of them here. But for now, this handles all of the syntax that we actually have. So I think for now, that's good enough. And I think the other test cases will pass. So I'm just going to move straight to doing a table-driven test for this. Okay, that seems to work. I'm not super happy with having to duplicate this code here. On the other hand, this is going to be a lot more complicated in the future than just this. So I think we can just leave it for now. It's only being duplicated twice, and I think a good rule of thumb is if you have it duplicated 3 or maybe even up to 5 times, then you should really strongly consider pulling it out. It's only 3 lines. Well, 4 lines if you include this. So I'm just going to leave it for now because I don't know how this code is going to look in the future. And I'm quite sure that this naive approach to code generation is not going to work for very long. So, yeah. So just to go over this code again, it's just going through each instruction in the intermediate representation. it's this will never happen in theory. So I could just replace this with an assert potentially, but I'm just generating an invalid instruction if it hits there. I'm ignoring the integer constants because they're handled elsewhere. In the case of subtract or add, I just look up what the left and the right is. If the left is a constant, then it moves that into a register. Then it asserts that the right-hand side is a constant and then generates the instruction for it. It's looking up the opdef and then the name of the instruction here. And then here is just the constant on the right-hand side. And then for the error instruction, it just checks to see if it's being passed in a integer constant. If it is, then it moves it into a register. Otherwise, it just assumes that it's already in a register. So error needs to return A0 to the operating system. Well, to the emulator, I guess, more like. So error is assuming that A0 has the return code, the error level, or whatever you want to call it. So this seems to work. We're getting assembly out. We should actually be able to replace this code now with code generation. So let's give it a try. Oh, I guess first we need to pull the code generation out into a separate file, I guess. There's really not anything there. So I wonder if we should just put it in ir.c for now and move it once we've got something more substantial. I think that's what I'm going to do. So let's just move this to here. I just realized I put the parser down here. That's the wrong spot. Should go before IR. There we go. Okay, tests are passing, and then essentially gauzy.c is going to be doing this. So and they all pass. Yeah, so for the first time in quite some time, we're using test.sh here to run the test through customasm and then through the emulator. So the emulator is actually running all the tests now, these tests right here. So that is good news. So you can see the first test program is running. It's just returning 0, which is this assert 0, 0 here. The second one is moving 42 into A0 and returning that. So that's this one right here. The third one is moving 5 into A0, adding 20 to it, subtracting 4 from that, and returning 21, which is what we're expecting here. And then this one is, well, you get the idea. So this one's being calculated correctly as well. And so is this one. Awesome. So, wow. We have a lot of time left on this video. I wasn't quite expecting it to be this easy. Why don't we check in the code and see what we can do from here? Now, why is this? Yes, but it is declared. Yeah, the linter just takes quite a while to catch up, but it is working. Yeah, it passes. So anyway, what to do next? Well, we've got test.sh here. It would kind of be nice to move from this to actually using test cases in the test binary. So Gauzy test here, and have our end-to-end tests as proper test code in C. Well, I do have some code. I'm not sure if it will work. So what this is essentially just a C wrapper file. Well, essentially it's taking the custom ASM crate from Cargo and wrapping it in a extern C. I can't think of the word. An extern C thing, whatever it is, and it's calling an internal function in custom ASM called assemble stir to binary, and then yeah, that's basically what it is, and it's invoking custom ASM, and then there is a nice C header file here that is basically exporting this to C. So in theory, then I should be able to compile all the way down into binary. Let's actually try it out and see if it works. I think I need to do this before. How big actually do I need that? Yeah, that should be plenty for now. All right, this is kind of where my C knowledge is running a bit dry. Says it can't find this. Maybe I have to do this. Oh, that seems to have worked. Ooh, that seems interesting. Oh, that's not. That looks correct. That looks correct. Oh, that's not quite correct. We need to code. No, that's not. That's their code. 51. That's what I'm expecting. Excellent. And then this should be 42. Yes, it is. Excellent, excellent, excellent. So this here just returns the error level of the previous program that ran. So now we're actually executing the entire thing end to end. So then this one won't work anymore because we're doing the custom ASM stuff here. So we could just alter this and just do Gauzy input like that. And all passes. Excellent. That's what I want to see. So then the next step is to, well, okay, first let me go over what I did. So in the code, what I did was I moved the buffer up here, and then I'm reading in the CPU def from here, this file here. So this tells custom ASM about the assembly language of, well, essentially the emulator that I'm using. It's my CPU. So we read that in, we read it into the buffer, and I enlarge the buffer so that it should be big enough. The CPU def is 9 kilobytes, I guess. So this is 64 kilobytes. It should be plenty big enough, but just in case we produce an error if it is too large, then I'm just adding a new line to the end of it just in case, and then null terminating it. And then here I just set up just some pointers to the end of the CPU def, and then I generate the code into the buffer. Then this is a custom ASM here. So that's producing the binary from the assembly code. So I pass in the assembly code here, and maybe it'll be clearer if I just call this assembly. And then it returns a binary. Then I run the emulator on the binary and save the code for later. I then need to free the binary because the binary was allocated within Rustland, and I need to return it to Rustland in order for it to be freed. And then I'm just freeing the other memory and returning the error code. And that's basically it. So we could add tests that do all of this. Let's actually just separate this out into a separate function, and then we can put it in another file somewhere. I'm not sure where. Yeah. Okay. The tests are still passing. So now we can move this into another file. What? Now it all passes. I must not have saved a file somewhere. Weird. Okay. Must not have saved the file. Oh, what? 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 Printing the source makes it work. And then without this, What? Now it's all passing. I almost guarantee you we've got some sort of weird memory thing that we're doing somewhere, because this is flaky. What? How is it passing now? I don't know. This makes me nervous. Welcome to C, where you can shoot yourself in the foot very easily somewhere. I'm sure I'll find it. Yeah, I don't know exactly where it is, but I'm sure I'll find it. Okay, so now we can actually move what is in test.sh here, and we can put it in actual C. So then we can move this stuff into C and do it there. So I think I'm just going to put it in Gauzy test, actually. So we might as well make some table tests for that. Bus error. Interesting. What's going on then? Is this flaky? Yes, it is. Okay. Yeah, here's the same flakiness, and it's happening in the tests too. Interesting. Line 104. So the IR is not correct. Init builder. Well, I'm not quite sure what's going on. I don't see the issue right in front of me here. Sometimes it's getting a segmentation fault. It gets through the first two examples just fine, but occasionally it'll either segmentation fault or it'll do random behavior here. I don't think it's hitting this issue here. I don't think it's this. Or at least I can't think of a way that it could be this, because we haven't touched this code. So it's got to be something else. Like if I were to guess, what's happening is, my guess would be that somehow the stack data is being overwritten and it's plowing into the source somehow, which I could probably test by just moving the source above here and see if the problem changes. No, it's still flaky. It's still doing completely random things. I either get a segmentation fault, a bus error, an assertion failure, or everything passes and it works just fine. See. All right. I don't think I'm going to figure this out for this episode, I don't think. Some of you who know C quite a bit better than I do are probably quite sure exactly what's going on here. I don't see it, not off the top of my head. I think I need to turn on memory sanitization and see what's overwriting what, because I almost guarantee you somehow or other memory is being overwritten past the end of something, and I'm just not seeing it. Like, I'm just not seeing it. I don't think it's here. It shouldn't be, because this is only 9 kilobytes. So it really shouldn't be here. No, because it's hitting the error before it. Like sometimes it's hitting an assertion error up here somewhere. So I don't know. And it's the weird thing is that it's flaky. I guess maybe it's doing address randomization, like it's putting things in different places. Yeah, I'm sure something is overwriting the end of a buffer somewhere, and I'm just not seeing where that is. So yeah, I will probably debug this between episodes because that's not the point of this episode. The point is to basically delete this file because we no longer need it. And we can do that. And it does occasionally pass. You have to try it a few times before it passes, but it does occasionally pass. So I can delete it. Yeah. It could also be that this is what's causing the problem in Rust, because I do have to do unsafe stuff in Rust. But like, I don't know. There's no way that that could happen because it's running after the assertion failure. So the problem has to be probably in the parser, I would guess. Right? Okay, I'm not going to figure this out right now. I could rack my brain for a while, but I think I need to figure out how to do address sanitization or something and figure out what's overriding what's memory. It's something's overriding something's memory. So I think that's it for this episode. Sorry to end on such a cliffhanger. I'm sure I'll figure it out between episodes. It's just such a funny problem to have. I seem to recall this from my C days. These were the fun bugs. Really, really fun. And I'm not being sarcastic there. These are usually quite illuminating. So yeah. If you have any ideas what the problem is, feel free to share in the comments. Maybe you saw what I did wrong. Fun little puzzle to figure out between episodes. So yeah, thank you very much for watching, and thank you for supporting this channel. If you do, it's very much appreciated. I am currently not working as of recording this episode, so it is very appreciated. Anything that you can spare, but no pressure. You do whatever you feel like. And yeah, I hope you have a great day. Bye.